Okay, hi everyone. I think we'll go ahead and get things started at this point. My name is Jim Sweeney. I'm the Director of Product Management here at Synaptica. Today we will be uh, listening to or participating in a webinar from presented by Bob Kasenchek and Aaron Leonard, specifically focused on the topic of ontologies for knowledge graphs. So we want to thank those of you who are joining us again, and certainly welcome to all those who are joining us for the first time. Just some quick notes before we get started on the actual presentation. We'll be looking at, of course, what I'm doing now, 5 minutes of introduction. The presentation itself should last about 40 minutes, and we want to leave plenty of time for a Q&A session. So we get all the questions in. Certainly, if we are unable to address your question during the session itself, during the webinar, we will be responding to those as soon as possible. We will also be recording the webinar, and following the webinar and getting that recording ready to go, we will send a link out to all participants, so you'll be able to review that as you want. And as I mentioned during the presentation, go ahead and use the Q&A button on your Zoom interface to submit those, and we'll respond probably a combination of both written responses, and we'll address some of those verbally at the end of the session as well. So a few just quick comments about Synaptica itself. We've been around for quite a while, over 25 years, I think over 26 at this point, in the knowledge management space, primarily providing software and services. We have several different software products that we offer in the space, and we also offer services around professional kind of consultancy and other services we can offer for those looking at developing, managing, and maintaining and distributing taxonomies, ontologies, and other knowledge management focused projects. We have always really focused on standards as kind of being our primary guides in developing our software, as well as the services we provide. And we also are always looking at the latest technologies. Certainly there's been a lot of advancement and really both standards as well as those different components are available to us to really tackle some of the problems that are evolving in the space. We really focus on supporting the work of knowledge workers within different environments, and those could be public, private, really across the board. Those people that are focused on different ways of managing knowledge and information across their organization, supporting information scientists, taxonomists, and ontologists. And we strive to establish really long-standing and very involved relationships with our customers, to be aware of what their requirements are, and also to address their future needs as those evolve. And just quickly, of course, our mission really to help people organize, categorize, and discover enterprise knowledge within their organization, and to help not only internal users, but of course everyone that's a customer of theirs and accessing that information. And as usual, this is really part of an ongoing series of different webinars that we are providing in these various topics. We'll continue to do that, and you'll certainly receive notifications on those, looking at different use cases and examples of using ontologies, knowledge graphs within organizations. And again, in this particular webinar, we'll be looking at the use of ontologies, specifically focused for the development of enterprise knowledge graphs. So with that, I'll go ahead and turn it over to Bob and Aaron, and we'll look at just a quick review. Bob is the Senior Manager of Client Solutions, and Aaron is a Senior Manager of Graphite product itself. So with that, please go ahead and take it away.
Thanks, Jim. We'll go ahead and get started. And good morning, good afternoon, good evening to everyone on the call. All right, so we'll dive right in here to the webinar objectives. So in this webinar, we're going to talk a little bit about what exactly are ontologies, what are knowledge graphs. Surprisingly, there's several different definitions. And then we'll talk about modeling ontologies for knowledge graphs, and then a little bit about connecting internal and external content and data. Just to set the expectation here, there is a ton of content we can cover. We've taken a high-level approach to some of this, given the time constraints, but we're happy to dive in a little deeper during the question and answer, and of course, follow up with any questions you may have after the webinar. So if we don't cover something as thoroughly as you would have liked, we're happy to have a deeper conversation with you on that topic. Okay, so what is an ontology? So let's quote directly from Wikipedia. And I'm going to start with, we're starting with this because we want to give you the difficult definition first. We think this definition is a little difficult. So Wikipedia states in computer science and information science, an ontology encompasses a representation, formal naming, and definition of the categories, properties, and relations between the concepts, data, and entities that substantiate one, many, or all domains of discourse. Now, if you're familiar with the subject, you may be able to unpack that reasonably easily. If you're not, this may be a little obtuse, and so we're going to help to clarify this a little bit, we hope. So when at Synaptica, when we talk about taxonomies and ontologies, we often refer to what we call a knowledge organization system, or KOS. And a KOS is a formal concept structure which defines a domain or multiple domains of knowledge. In most use cases, an organization is trying to describe what it knows and what it wants to know. So this can be very organizationally driven rather than sort of open world driven. Ontologies help us to understand how concepts, people, places, products, processes, and organizations, they all relate to each other. Ontologies can also be used for things like inference, machine learning, connecting disparate systems, and of course, as we're going to get into in this session, knowledge graphs. So hopefully this diagram will help a little bit to unpack what we talk about in ontologies versus taxonomies. You may have heard somewhere out there that an ontology is a taxonomy on steroids, or something to that effect. And we don't really like to think of it that way because although ontologies can be progressively more complex than, say, a list or a taxonomy or a thesaurus, it's not necessarily so. An ontology can encompass these various kinds of vocabularies. So we like to talk about an ontology as really being a combination of two things. The ontology is the schema, the semantic schema itself, which includes the scheme, the property types, the relationship types, the classes. It's the defining upper level for how your knowledge organization system or ontology is structured. Whereas a taxonomy really is defining the very specific concepts, named individuals that go into that ontology. So for an example, you might grab a public ontology that talks about the properties and the relationships, and you provide the detailed concepts that go into that ontology. So again, we'll get into this a little bit. Hopefully we're building progressively as we go to a greater understanding. And one of the ways we're going to try to do that is to show you some visualizations of ontologies. Hopefully this helps to understand what an ontology is and how it relates to a knowledge graph. So one way an easy way to think about an ontology, or a helpful way, is to consider the entire structure as a graph of nodes, as you can see here. In this case, we have concepts and relationships that are interrelated. On the left-hand side, you'll see what is a hierarchy, which may look more familiar to you as if you're familiar with taxonomies, that we've got some structure there. And in this particular organizational project here, what we have are 4 vocabularies. One of them is separated into 3 separate schemes, which is called the GACS Agri-Semantics vocabulary. Then we've got the GEMET thesaurus, we have Google products, and we have the North American Product Classification System. All of these thesauri, all of these vocabularies or knowledge organization structures are available publicly. And we've brought it into this tool here and sort of interrelated them so we could visualize how these things might connect together. And what we've done in this particular instance is we have taken those different vocabularies and we've modeled it in such a way that different or similar or exactly matched concepts, because there's some overlap in these ontology models. What we've done is we've mapped them to each other. So you'll see things like same as, because the concept is the same in two vocabularies. And so we're doing several things in this particular instance where we're saying, here are relationships between concepts that have some kind of relationship, which may be specific. And then we're also saying there are some concepts that are exactly the same or for our purposes are the same. And so we're mapping all of these together. If we go down a further level, okay, we're kind of zooming in here. If we zoom in from the project down to those scheme levels, now we're looking at, these are some individual concepts here. And you can see that these concepts are coming from various vocabularies. They're interlinked. I've got all of these relationships drawn as lines between these things. And if we start to build out this thing, we can see other things. So for example, here's a collection. And a collection, this collection in brown, which says tropical fruit, is a collection is a label that can unify concepts which may live in one or more schemes. It may live in different parts of a vocabulary. You're sort of grouping them together. So here I've got passion fruits and passion fruit. Those are coming from two different schemes. I don't want to make them hierarchical, but they not only have a relationship, which is same as, I'm also including them in the same topical grouping called a collection here. If we zoom in even more, we can start to see that in orange, we have schemes. And these schemes are representative. So you can see the complexity here. So we're not trying to overwhelm you with complexity, but trying to show you instead how you can start to traverse through this graph-oriented structure and start to see the interconnectedness between these vocabularies and how it relates to those very small level or detailed level concepts that come from a taxonomy, like passion fruits in this instance. And all of these are based on triples. So a triple is a combination of three elements. It's a subject, a predicate, and object. You'll see there I've got in brackets verb. The easy way to think about this and what makes it semantic is that it really follows, especially if you are an English speaker, this is the way our language is structured: subject, verb, object. That's the basic premise of our language. And not all languages follow this, by the way. In fact, most languages are not in this order. I think it's subject, object, verb. But for English speakers, we have this natural semantics where we have a subject, a predicate, an object. It's very sensible to our mindset because it's the way we speak. These have different names. So in the world of graphs, these are called nodes and edges. And you'll see there it's labeled. We've got two nodes connected by an edge. And then finally, you can also call these entities and relationships. And these triples can model many kinds of basic information. So here I've zoomed in, and again, I've got, these are different concepts, but I've zoomed in on some concepts with some basic relationships. So every entity in an ontology is either a subject or an object, and these are connected by those predicates, or as we call them, relationships, which are essentially these verbs. The relationships or predicates, these are objects of their own as well, and that's an interesting concept. You can treat them as an object. It's not just the relationship, but that's something about triples and graphs, is that these things are objects with their own URI, a universal resource identifier, which so everything can be treated as an object and pointed to. And also that allows it to be adopted and used, say, by other ontologists or other organizations if you were to build an ontology and make it public. Okay, so, and these relationships are defined as being reciprocal. They don't always need a pointer back. So here, for example, we've got has broader, has narrower. It's a two-directional. They can be unidirectional, but the other direction is sort of defined by the nature of defining that relationship in itself. So if we look at this, we see that, again, we've got subject, predicate, object. Now, of course, it depends on where you're starting from, right? If I start from chemical element, then that's my subject. If I'm sort of, and I put this in quotes, starting from transition element, then that's my subject. And again, we go subject, predicate, object. And again, all of these items are triples when taken together. So as more triples are created and connected, they are organized into an RDF, and that's the Resource Description Framework standard. We're not going to dive too deep into that. We'll talk a little bit about it. And this RDF graph is stored in an RDF graph database, which is also called a triple store. So, as I've already mentioned, relationships describe the nature of the connection between concepts. So a hierarchical taxonomy really, strictly speaking, only has one type of relationship, and that's hierarchical, broader to narrower, parent and child to these terms. So in the SCOS standard, again, we'll cover that in just a minute, just briefly anyway, the broader narrow relationship is defined as SCOS broader or SCOS narrower, and we can label it with a label name has broader, has narrower. So that's pretty basic. So here we've got a parent and its child. Subtropical small fruits has the child or has a narrower term, passion fruits. Okay, so thesauri, and in practical use for most of us, taxonomies, include equivalence relationships. And you may have seen this as use for. That's sort of a basic in the standard that you have these. Here, we've modeled this using an OWL relationship called same as. We've said passion fruits is the same as, for our purposes, the term passion fruit. Okay, so again, a lot of this is kind of basic stuff. If you're familiar with taxonomies, that is. Thesauri also include associative relationships. Now here we've got has related, and I've defined a custom relationship called has confluence page. So these hierarchical, associative, and equivalence relationships link things to other things. So for example, a conceptual relationship in an ontology, like has confluence page, can link to a tangible content asset in an internal or external systems tagged with metadata concepts from that ontology. So here we literally have a confluence page called passion fruit, and it is linked to an ontology in an ontology management system. So we're really bridging the gap here, that these are things. The concept is a thing with a URI. This page is a thing, which also has an identifier and a location. And we've actually modeled that in the vocabulary. We have a stub in the vocabulary that says passion fruit, it's a confluence page. And when I click out, I go to that system that has that page. So we're talking about sort of real world or things that are quote unquote out in the world. They are identifiable, tangible things that you can kind of link to and get to. And that's important to the idea of, or notion of, a knowledge graph. Let's go back to definitions. Pascal Hitzler wrote in a pretty recent article here. We like this definition. He says, in a semantic web context, ontologies are a main vehicle for data integration, sharing, and discovery. And a driving idea is that ontologies themselves should be reusable by others. We really like this quote because we agree with this summary. It's very concise. It goes to the heart of being standards-based, and it's about interoperability and shareability with ontologies, linking things that are available in the public to your own proprietary information, which you may choose not to share. But the reusability aspect is quite important to this notion, and the connectability between these ontologies allows you to build and develop a lot of applications on top of a lot of purpose-driven enterprise applications. So back to our image here. With these ontology relationships. So we mentioned SCOS. So now I've changed my labels from what type of relationship is a broader hierarchical relationship to where it came from. So this relationship came from SCOS. SCOS is a standard based on RDF. Again, we're not going to dive deeply into SCOS and what it's all about. You can research that on your own, or we can discuss that a little further after the presentation. But SCOS is a standard. And what's nice about SCOS is that if I adopt SCOS and you adopt SCOS, then we both have a relationship called has broader, has narrower. And that's interoperable. And that's a wonderful thing, or we think it's a wonderful thing. OWL is the same way. OWL is also defined as an RDF standard. Again, we're not going to dive deeply into the difference between OWL and SCOS, but I've mixed and matched here. And what I've done is I've taken an OWL relationship, same as, again, this is a standard relationship defined in the OWL standard, and I have included that as well. So as we move and we go to our next thing, we see that I also have I've made up custom relationships. These are ones that I have created myself. So has related is a standard, but product of is something that was probably designed specifically for one of these vocabularies that I've adopted. And then I've created my own custom has confluence page. And what's really wonderful about using this is we're using standards to define relationships that are common. And then I'm defining my own custom relationships and I'm using them together, which is a really nice thing because then you can start to define quite complex ontologies using publicly available things as well as things that you've defined yourself. So again, connecting to that internal and external content. Now, if I go here and I start to look at how this looks, if I use publicly available ontologies following the W3C standards. W3C is the publisher of RDF and SCOS and all those standards. And I start creating my own ontologies using those same standards, right? I'm pulling from these public ontologies, SCOS, OWL, FOAF is friend of a friend, Dublin Core is DCMI, Mesh, all of these different ontologies and standards that I can mix and match, create my own organizational ontologies so that when you make your organization ontologies, we can theoretically, if we choose to, connect them or see some portability, interoperability between them. And if you think about it, if we have an organization doing one line of work with an organization doing another line of work, but there's overlap between them or there's connectability, to be able to connect those ontologies, make them public, assuming that the information is publicly, that it can be made publicly available, then you can start to interlink these things and make a richer semantic experience for end users. So this is the ontologies portion. Just to recap, so ontologies are really a great representation of and between domains of knowledge. They can bridge heterogeneous information sources, especially based on standards. They are supported by standard portable formats. We're a big believer at Synaptica of standards. Their native RDF, which is important for triples and the whole nature of building graphs based on this RDF standard. We think that's also important because it is a standard and it is interoperable. They allow for axiomatic reasoning, graph traversal, inferencing, very complex kinds of semantic and other kind of application building possibilities with ontologies. We can include custom relationships in classes. So we can define things that are shareable, that are an RDF standard. We can also define things for our use case and either use that as proprietary within an organization or make it public for reuse for other organizations. And you'll see that. One example is the BBC. BBC publishes their ontologies for public use. These are, again, the ontologies, they're the relationships, the properties, not the items that go in them. And they've shared that out, and you can go grab those and reuse that structure and populate it with your own concepts. Finally, we believe that an ontology-first approach to knowledge graphs. So we believe that ontologies are the foundational layer for enterprise knowledge graphs. So now I'm going to hand it over to my colleague, Bob, and he's going to continue with the discussion on knowledge graphs.
Thanks, Ahren. Hi, everyone. So with any emerging technology, it takes a while for the industry to fumble around and agree on a definition. So in a parallel structure to Ahren's part of the presentation, talking about ontologies. I'm going to start with some foundational definitions of knowledge graphs and see if we can tease them out into something that we can understand. So doing some research into what people are calling the definition of a knowledge graph, we found one from a recent paper by authors named Erlinger and Voos, which is referenced at the bottom, which is that a knowledge graph acquires and integrates information into an ontology and then applies a reasoner to derive new knowledge. We like this definition, and we're going to try and tease it out a little bit. The central idea is that knowledge graph is an applied ontology, and it's an ontology that's been connected to data and or content, includes the principle that initial information can be inferred or reasoned from the graph, and more on this later. But first, let's talk about the basic principle. So our partners at Ontotext formulated this definition, which we found to be a little easier to understand, is a little less computer science-y, is that a knowledge graph is when an ontology is applied to a set of individual data points, and those data points can be HTML objects in linked data that you can grab information from. It could be content in a content management system or anything in between. So a knowledge graph based in an ontology is made up of interlinked entities described in a formal structure, which is what Ahren was discussing in his part of the presentation, so that they can be used by both computers and people. So specifically, semantic web researchers' methodology is to create knowledge graphs, data structures where entities are uniquely identified by URL and linked to other entities via triples using a language called RDF. So that very much like what Ahren was describing. So in a lot of ways, a knowledge graph is an applied ontology. Simply put, a knowledge graph connects an ontology, which is an abstract structure defining the relationship between topics and entities, to data or content, so that the objects in the ontology are pegged to real-world entities represented by URIs. So that an object in your ontology called content, instead of just being an abstract node sitting in a computer system somewhere, is actually relatable to an actual content object. Or if it's a term in a taxonomy, then a topic in your ontology to more information about it by linking to definitions or a Wikipedia page or a linked data source, or an author to their website or an institution to their unique identifier. So when you take an abstract ontological structure and then connect the nodes to real life objects, and by real life objects, we mean things with URIs, web pages that can represent other objects, then we've created a knowledge graph from our ontology. And the idea is that this information can be surfaced alongside content to provide additional information about the content or topic. So most people, including me, first encountered knowledge graphs via Google, as in the examples we'll see on this set of slides and builds. When Google deployed their knowledge graph, instead of just getting a list of content that matches your search, they enhanced the search so that when you search for something in Google, you get on the left-hand side a set of documents that match your search terms, and on the right-hand side, you get that little card, which comes from the Google Knowledge Graph. So that searching for content, which is to say web pages, about a subject brings up both the list of relevant content of web pages, and it's augmented by information about the topic in that knowledge graph card on the right, which can and often does include a definition, a link to the Wikipedia page about the topic, links to other websites about the topic, images like this example about passion fruit. Then depending on what the topic is, it could link to an IMDb page about movies and authors. It could have questions, recipes in the case of passion fruit, or even nutrition information, and other kinds of content. So that the revolution that they sparked when they did this was marrying content with information about the topic that you searched for, so that you can dive down into the web pages that you got as results, or you can dive into more information about the topic. This is achieved by having a graph of concepts that can quickly be related to content. And it's Google, so there's massive processing power, so they make it look very easy. And then number two, by connecting to other sources like Wikipedia or sources of images or recipe sites, IMDb, a nutritional site, and all kinds of other things. By equating the concept, in this case, passion fruit, in Google's graph, with the node passion fruit in other data sources, and then surfacing the content alongside the other information. So this very sort of simple revolution of the Google interface provides a rich search experience, all driven by an ontological graph connected to content on one side and data on the other side. Managing information and content in this way creates an information ecosystem. So as we've been pointing out throughout the presentation, ontologies are the foundational layer for a knowledge graph. So simply put, a knowledge graph is the combination of an ontology and content or data, which may live inside your organization in a content management system, in a DAM, in a shared drive, and perhaps combined with information living outside your organization in either public or proprietary paid sources, such as Wikipedia or linked data sources like DBpedia or Wikidata, or anything else that you can connect to via persistent URI to add information. So the ontology is the basis for the graph. You connect the objects in this abstract structure, the nodes of the ontology, to data sets or content sets. Some will be inside your organization, some will be outside your organization. So this slide is sort of a very high level abstract diagram of how the information in the ontology management system, which is again the abstract nodes and lines graph, connects to information, stores that information in a graph database, and then those nodes can be concretized by connecting them out to data sources. Such as a taxonomy and other vocabulary, sorry, Ahren, lists, content repositories, and a topical index to create a knowledge graph. So that documents, databases, websites, and people internal to the organization can be combined with information outside of the organization, all connected by the ontological structure as the common domain representation that ties it all together. And then, of course, you need a presentation layer or a UI for someone to be able to explore this. We'll talk a little bit about that later. Now, this, of course, as this diagram very vaguely suggests, does require some systems integration. You have to connect these data points and make them talk to each other. But ontologies are structured in a way, as Ahren mentioned, that's very interoperable, and they're designed for this kind of integration. So although there's a lift to do there, the very nature of the structure and the way we store the data makes that lift a little easier, because the interoperability and extensibility is baked into the ontology standards. Okay, go ahead. So by itself, an ontology is the structural underpinning of the knowledge graph, and the concepts in the ontology are the interlinked entities in the abstract graph structure, which can then bring in additional information as attributes. So the ontology is the structure that connects the metadata, the content, the structure, and the data. And when an ontology is put into action or applied through representation, visualization, querying, and reasoning, now we've got a knowledge graph. So we're trying to work through the working definitions that we found out in the industry and land on something that's concrete. So in addition to the ontology management system, which is represented by the screenshot of the hierarchies from graphite in the middle of this diagram here, and the backend graph database, which holds the triples that are surfaced in an ontology management system, there are external and internal systems and sources that you will need to connect your ontology in order to implement it into a knowledge graph, to connect it to data and content. So things on the left-hand side of this slide are internal sources, things inside your organization, and things on the right are outside your organization. So on the left, you might have a database of people and organizational roles. You might have a shared drives or content management systems, document management systems, and an interface to search, which could be a traditional search interface enhanced by knowledge from the graph, or it could be some kind of graph-based interface. On the right side, we have external sources like public repositories of content that you can link to, paid systems and libraries, proprietary organization, and public and paid databases of other kinds of content. These include linked data sources like Wikidata or DBpedia, as well as Wikipedia. Anything that has persistent URI links that you can point your nodes to as objects to connect the abstract structure to concrete objects in the world. Again, in a world where object means a thing that has a persistent URI. So let's look at some examples that I hope are going to make this even a little bit clearer. This example is an ontology connected to content, so a very small knowledge graph that I modeled based on data from PLOS, the Public Library of Science. I use their data because they publish it all as open access and anyone can go look at it. So the thing that I've modeled here isn't proprietary. It's information that anyone can get off their website. And this basically models a simple information ecosystem in scholarly publishing. So in the center of this diagram, we have a node that represents a journal article. That journal article is defined by a DOI and a persistent URI. That article then has authors, which are I don't know how well the colors are showing up, but sort of up and to the right, the light brown nodes. And those authors each have an object in the system that connects to a real life entity, and they all have an affiliation with an institution. Down at the bottom of the graph, we have the article connected to some topics about the article. This one's about chromosomes and genomes and some other stuff. Over to the left, we have the article, the journal that the article was published in, and then the publisher of the journal. So this simple ecosystem shows the abstract relationships between the article, the content article, the authors, the topics, and the publisher and the journal. That we concretize by linking each of these things out to a real world entity with a URI to make a knowledge graph, so that not only have we represented the abstract structure of what's going on in this information ecosystem, every node in the structure connects to something that either resolves into a website, produces a piece of content, connects a topic to more information about it, or some unique identifier in the case of authors that you can go find more information and query and add it to the graph. So crucially, the revolution here in this kind of content management is that instead of a table with a bunch of content that have tags applied to it, the metadata and objects being modeled are objects in the graph because we want them all to be part of the knowledge graph. Go back to the previous slide, please, for a second. This is philosophically and structurally fundamentally different than a relational database-based model in which information is stored in tables, because as Ahren says, the lines in this graph are just as much data objects as the nodes are. In a relational table with key value pairs, you're sort of inferring the relationships between things. I have a table of authors that's connected to a table of content. Here, the relationship between the author and the content is an object that we can name, and it has its own properties. And that's structurally fundamentally different because the relationships are first-class data citizens in their own right. Another important point here is that the actual content object, that journal article, doesn't live in my ontology system. I have an object representing it in my ontology system. That document lives on the web, but it could live in a wiki page. It could live in Confluent. It could live in SharePoint or a CMS or a DAM. So the object in the abstract structure in the ontology represents an actual real-world object, but the ontology system is not a content management system. You don't manage your documents there. You have a node representing the object that then you connect to real world, again, for values of real world, that is the web, because they're URIs. So they're all represented in the graph. So at its simplest form, that might be the page or the document that's linked to is an object in a triple or anywhere in the graph, but it gets richer when the page or document's not just an outbound link, and if it's expressed as linked data, the graph finger quote knows more about it, and you can pull information about it to do analytics and inferences. So let's go to the next slide. So this is a blown out example of that same information ecosystem with some more information added. So this is the same content object. On the left, it connects to the journal that published it, and that publisher has a bunch of other journals. And I wanted to keep this small for purposes of displaying in a webinar, but all of the yellow topics on the bottom could be also linked to the papers about those topics. The authors in the upper right would be linked to all of the other papers that the authors publish on. So if you take all the hundreds of thousands of papers in the PLOS corpus and attach them to authors and topics and all of the journals that they publish in, now we have a representation of an entire ecosystem, a total view of the publishing ecosystem, where every object in the publishing ecosystem is represented in the abstract structure of the ontology and then connected to real-world objects via URIs to create a knowledge graph. This is great because it allows you to do Google Knowledge Graph-y like things like surface topic pages next to content, or be able to query information from your graph and do inference from your graph, about which we'll talk more in just a second. Go ahead to the next slide, please. So the data model can contain other information about these objects. So this slide is back to the same slide, the smaller slide about the publishing graph from 2 slides ago, but to show that each of these kinds of data objects, which we could call a scheme, has additional fields associated with it that aren't relationships to other objects in the graph. They're just metadata about the object that we can store in the system. So even though we know the author, Spencer Gordon, published this article in the middle here, we can also store his name if he has a personal website, his ORCID, which is a unique researcher ID, and any other information that you want to store about the author. And the same goes for the article. The article has a title, it has an abstract, it might have references to other articles, it has a DOI, which is a unique number, and so forth. So every object node in your ontology, in addition to being connected to other nodes, they can have metadata stored. It's a database, it's a graph-based database, but you can store any information that you want about the authors. So the model allows for relationships between the objects and links to external data sources that can provide more information about each node that can be discovered via URI links. But if the data is structured, you can also pull it directly from those linked data sources and ingest it directly into the information in the graph. This principle, the linked data principle, is very important and forms the basis for much of the documentation and standards about ontology construction and interoperability. So returning again to the smaller example, now we have an ontology describing the objects we're interested in. This is the data model, but it doesn't do anything if it's just sitting in your ontology system. It's abstract, so it's populated with attributes, as we saw on the previous slide, and connected to both internal data, like content, and external data, like a Wikipedia page or a linked data source, information sources that we've been discussing. So now all this information is included in the graph, and we can ask questions about our data, like how many articles on genetics did we publish last year by authors from Harvard? I'm sorry, I'm having trouble seeing over there. Or what's the average number of authors on a paper about mathematics, or other information that you might want to query from your data. So querying a graph like this can be done directly in the underlying graph database using a language called Sparkle, which definitely is not the topic of this webinar, but it's more likely that users will not be familiar with a query language and that they'll need to have some other interface to query the data, like we see all over business applications on the web with relational tables and query languages. So it's very easy to stand up dashboards for non-query language users to explore and query business data. End user, that is non-technical end user applications for graph exploration, are an important piece of the puzzle. And they might look something like our visualization tool here, where you can drag nodes around, double click them to expand them and explore the graph by walking the graph, we call it. Or you can have something where you can build a query to try and ask specific business questions by standing up a dashboard. So this allows us to walk the graph to find information and explore the data set without learning a query language. I think I went through this. Go ahead. Okay, so one important point that we glossed over earlier that was in one of the definitions is that RDF graph databases allow you to infer connections between objects in your graph that are not explicitly described to glean new information based on the logic of the graph and its relationships. So in this example, which is the same little publishing example about that one article and its authors, the article, which is in the center, has 4 authors and 2 topical tags. Those are the 4 authors. It has a journal and it has 2 tags that I have applied to it. So since all of these authors wrote the same journal, we know that they're co-authors with each other. So even though we don't, in our original data model, have something called is co-author and connected these things to each other, we can do that automatically. We can write a query that says, if these authors wrote the same paper, they are therefore co-authors on this paper. And we can either take that information and go do something with it, or we can actually add that information to the graph to establish no relationships. So we can say that these authors now in my emerging orange line have the relationship, are co-authors with each other. And we can add that information to further enrich the graph. In the same way, we can say, well, this author wrote this paper's about chromosomes, therefore we can infer that these authors publish on these topics. So now we can say, oh, well, the topics are applied at the paper level, but since the author wrote the paper, we can say this author writes at these topics. And then we can ask a question like, well, what topics does the journal PLOS Genetics publish on? Which the name probably gives it away, but from the graph, we can also infer that because this paper's in this journal and this paper's on these topics, we can infer that this journal publishes papers on these topics. So we can query additional information that's not explicitly represented in the graph. We can query it off and run with it and do something with it, or we can add it to the graph as explicit new relationships of information to keep enriching the information in the graph to make it more useful. Now, of course, you have to have done careful modeling in order for this to work, because the garbage in, garbage out principle still applies. But if you do careful modeling, you can infer this additional information and add it to the graph. So, sorry, there's the animation. So very briefly, to sort of try and bring this back to the system level, in order to implement an ontology into a graph, and then in order to implement the graph to be useful, there are systems and applications that have to be integrated. This sample diagram of one possible systems architecture is intended to show some of the primary components. So in the center, we have your enterprise knowledge graph, which is powered by an ontology management tool, our program Graphite in the upper left. That's all stored in the graph database, which can then be accessed by inferencing and analytics points, API web services to build business applications, and then be connected to internal and external databases, other databases and data sources, in addition to content sources, and perhaps a content management system, a digital asset management system, or a wiki environment, or something like that. So in our model, the graph sits in the center of this information ecosystem because it's drawing in data and points. It's pointing to and being pointed to by various kinds of systems that either want to answer questions based on the graph, add new information from the graph, or connects to other data sources from the graph. So integrating an ontology with other systems can create a powerful information architecture framework describing and unifying concepts from your ontology to databases and analytics endpoints and other things. So after trying to cover a semester's worth of material in a webinar, to sum up, ontologies are the foundational structures for knowledge graphs, but ontologies are abstract entities that, if not connected to external data points, are just sitting in your ontology management system. And an ontology is modeled to represent a domain or domains of knowledge, the objects in those domains, and the relationships and connections between them. The semantic relationships between concepts and domains of knowledge are the same as relationships between the concepts, domains, and content. And in order to explicitly model content and data models, an explicitly modeled ontology is essential to express unambiguous metadata terms and relationships. And then a knowledge graph connects an ontology to data or content in order to provide business applications, answer questions, or just store information for querying and browsing. So all of these topics have a lot more information, but in the interest of time and the scope of the webinar, we're going to stop there and see how many questions we can answer or have a discussion in the time that we still have left. Thank you.
Okay, great. Well, thank you very much, Ahren and Bob. Yeah, as Bob mentioned, we're reviewing questions in the Q&A section and have answered a few of those, but we'll go ahead and tackle some of those now. So if Ahren, Bob, you want to go ahead and address any of those, please do.
Yeah. So I'm gonna tackle one of these. Can you speak to the added value that Synaptica provides to cloud-based MS Office 365 suite and their enterprise social graph? So I can tackle some of this. I'll be straightforward and honest, I don't know the ecosystem of Microsoft so well that I can directly speak to the enterprise social graph, but I can give you enough information, I think, as a starter. So when it comes to Microsoft, we have a dedicated connector between our tools and say SharePoint. Because that's where, and I believe that Microsoft still, even in their iterations, are pulling that metadata still from that core concept of the term store. And so really the reason or the driving use case for having an ontology system putting terms into something like SharePoint is that SharePoint was not designed to be a robust taxonomy management system. Yes, it can manage metadata. It's got the term store. It includes a hierarchy. It includes synonymy, right? It has some of that basic functionality, but it's not particularly robust, to be very blunt. If they are still using that as the core to build their enterprise social graph and connect all of this content, then really you need more robust relationships. The real problem is we can't, with our tools, we can't force those relationships into per se. We can't force those relationships into SharePoint because it doesn't really handle them. So you have to come up with an integration where you're putting not only the concepts, but you're doing a little bit additional work to include the relationships between those concepts so you can really power the relationships between things. Again, I don't know Microsoft, their advances well enough to speak to it, but essentially the principle is the same. They are using metadata as a driver to connect various types of content and people and all kinds of objects within the system to each other to build a graph. And so how Synaptica or an ontology management system tool would play into that is to be able to make that vocabulary centrally controlled so that one thing that I don't mean to say anything too bad about Microsoft, but one thing that, in my experience at least, I'll just say that, they are not particularly wonderful about playing well with other tools, other systems necessarily. There's some work involved. So if you think of it this way and you go back to that information architecture diagram and you set something like Synaptica at the middle, Graphite, you say, I've got an ontology that connects my SharePoint with my other content management system, or my digital asset management system, or my non-Microsoft systems, then you are being able to create a graph that goes between Microsoft and other systems, not just within the Microsoft ecosystem. So I think that's about as far as I can go with that topic as far as my knowledge. And then we can Bob, if you want to field one of these other questions that's come up, maybe the one about that Daniel has asked, Daniel Alva, where he's asking how to start building an ontology overlay between different taxonomies when the knowledge has been built and is operational. If you want to maybe try tackling some of that.
I'm trying to catch up on the question and answer tab here real quick.
Yeah, if you go to the answer tab in the Q&A, you'll see Daniel's question.
While Bob's looking that up, Ahren, there's one that's come in the chat instead of the Q&A. Major differences between taxonomy and ontology. If you can backtrack to the slide that has the ontology embracing the schema and the taxonomy, that might be a way to address that question.
Yeah, let me get back to that without exiting out here.
There we go.
Okay, so yeah, so again, I'll double back to what I had said before, which is there was this kind of notion that an ontology was just sort of a taxonomy with extra stuff in it. And we really don't think of it that way. If you go out and look publicly, a great example to help you understand the difference would be go to BBC Ontologies and see what they include in their files. Like if you literally go and download and you just sort of, it's not so necessarily easy to read RDF or XML, but it's basically understandable even if you're a non-technical person. Read what's in that file or upload it into a system like Graphite. And you'll see that it's the container, if you will, for more specific values. They're providing you with the properties and the relationships, the definition between things, but they're not providing you the things themselves. And the things themselves live in a taxonomy. Those are the concepts, the actual. So my concept called passion fruit in the example is a concept that really lives in the taxonomy. The ontology is that scheme to say, how can I relate that concept to other concepts? How can I relate that concept to other concepts within a scheme and between schemes? How can I relate that concept to things that don't live within the ontology management system? So really it's about defining that schema, that upper level, versus the things themselves, those very specific concepts within it. And so hopefully that will be helpful. And Bob, if you want to maybe field that question from Daniel, if you could see it, this is about start building an ontology between different taxonomies when the knowledge has been built and is operational.
So one way to think about that is that an ontological and upper ontological structure is a very useful way to bridge the gap between different taxonomies. That could be an equivalence relationship, as Ahren described, where concept in taxonomy A is the same as or nearly the same as concept in taxonomy B, or where they feed different aspects of the same thing. So in my tiny ontological publishing example, maybe you have a taxonomy or an authority file, a flat list of authors, one of journals, one of topics, one of concepts, one of content. And the ontology is a way to tie those things together by expressing custom relationships between them. And one of the nice things about ontological and graph-based systems like this is a lot of organizations that are moving in this direction are using them not as a replacement for their legacy system, siloed content and databases and various silos across departments. You hang an ontology sort of as a mobile on the top of it. I'm making gestures like you can see my hand, but and it connects all those existing systems without ripping and replacing them. The ontology can tie those data systems together. So existing taxonomies describing different facets of things can either be equated to each other or they can be linked to content objects that already live in other systems without having to tear them out and do a big migration and ETL and all those things. The ontology can come in and lay over the top of those things. I'm not 100% sure that I answered the question.
Okay. And just for time's sake, we can say that we might be able to stick on a little bit longer to answer some of these questions. I'm going to try and answer one quickly here as we get to the top of the hour. How do you model statistical data in an ontology? That's a great question. We sort of think that there's things, okay, so from a UI perspective, I'm a taxonomist or an ontology and I'm looking at a tool and I'm doing a UI, the answer is probably you don't want that kind of data. I don't want product numbers in my ontology itself. In a viewable hierarchy. Same thing with statistical data. That's a massive amount of data. And does it help you to look at instances? And how do you model something like that? How do I even look at something like that when it's at the individual level, especially if you have something like, here's person A and here's their social security number and here's this data and that data. A lot of that would be handled either in place where it's at, in some other database that's connected on the back end to a graph database, so that you are integrating with the ontology, but you're using the ontology as sort of a filter or a higher level category to say there's data behind this and there's a lot of data behind it, but I don't need to model or represent that necessarily in the UI, because you can imagine how troublesome that is, how problematic that is. If you have a million entities, does it do you any good to look at it through UI? Really, if you can't really traverse it and have a good presentation of it hierarchically, that's kind of a mess. So you may want to connect that. You do connect it to your ontology and you're tagging that data, but you're not necessarily representing it through the UI. So hopefully I've answered it that way.
Thanks.
Yes.
Sorry. There's some modeling choices there, and it depends on what kind of questions you want to ask, what things you want to make an object in your ontological system, and what information you want to capture in a field related to that object. So let's say you have people and their social security numbers. Like, it seems to me that in most cases, the social security number is a field that lives in the node about people instead of an object called social security number, because those ideally are one-to-one. No two people have the same social security number. Social security number is one person per number. So that ontology would be a bunch of one-to-one nodes. So it doesn't make a ton of sense. Now, for statistical data, it might make sense to have it in a field as or an object, but there's some modeling choices to be made that are going to affect what kind of information you can query and what kind of inferences you can draw, how things are stored in the database, what's an object, and what's a property. So that's a lovely conversation that I think I just wanted to sort of touch on.
Okay, great. Well, let's, given that we are a little past the top of the hour, I think we're going to wrap things up. I certainly, again, want to thank you all for joining us, those that are still on. Thank you, Ahren and Bob, for a great webinar on what really we've seen is a very large topic, lots to talk about. And as Ahren mentioned at the opening, we're really just scratching the surface on a lot of these descriptions and use cases, and really the applications of where and when ontology and knowledge graph information, how it intersects and where it can be used. Again, any question that we didn't get to via either the Q&A area or live, we will be following up with each and all of those. So we'll get you an email or some other kind of written response to any open questions. And we would encourage you also, if you have any deeper questions, you'd like to have a conversation, we are happy to do that. So you can reach out to us at that email address on the screen, info@synaptica.com. We'd love to speak with you about any specifics that you're interested in. So thank you all again. Do stay tuned for additional webinars we'll be providing over the course of the rest of the year. And we hope to hear from you or speak with you soon. Thanks very much.